All right, so looking at this AP style question, and this is not an official AP exam question. It's a question that somebody out there made for her students to prepare them for this weird 2020 coronavirus AP exam. Um, Question A, actually, you won't see something like A on the AP exam because it can be done explicitly in the calculator. And they're going to try to word the question so that calculators are not really going to be an advantage. And it is a clear advantage on this one because you could just find the derivative of f at 2 using the derivative at a point command, but we will, for the sake of practice, actually find the derivative. We're trying to find the slope of the line tangent at 2, which means f prime of 2. So the derivative of ln 5x would be 5 over 5x, which I believe would reduce to 1 over x. And the derivative of sine is cosine pi over 2x. I'm going to go ahead and put a pi over 2 in front for my chain rule. That's the derivative of the inside. And so if that's f prime of 2 would be 5 over 5 times 2. That's going to reduce to 1/2 minus pi over 2 times the cosine of pi. And cosine of pi is -1, so you could clean this up to 1/2 plus pi over 2. Don't have to clean it up at all. You can leave it as 1/2 minus pi over 2 cosine pi, but I chose to simplify it some. Looking at B, introduces a function k, and here they want you to find k prime of 3, and so we will have to do the chain rule, and this is a little bit more like what I expect you to see, on the AP exam this year, because a calculator is not going to help you differentiate f of g of x. You're going to have to recognize that that's going to be a chain rule, and you're going to have to do that completely on your own. Calculator won't help you get that derivative. And so now I'm going to find k prime of 3, which will be f prime of g of 3, g prime of 3. And when I evaluate my g of 3 and my g prime of 3, g of 3 is 5, g prime of 3 is 0.6, and now I need to find f prime of 5, which is similar to question A. So I'm going to come over here on scratch paper. F prime of 5 would be 5 over 5 times 5, that's 1/5, minus pi over 2, cosine of 5 pi over 2, and cosine of 5 pi over 2 is 0, so that would just end up equaling 1/5. And so my final answer is going to be 1/5 times 0.6, and I see no need to clean that up. It would simplify a little bit if you want to, but I'm not going to bother. And then question C brings in probably one of the most anxiety-inducing types of derivatives. It's an inverse derivative. You are told that m of g of x is equal to x, and that alone should tell you that they are inverses. That's your algebra definition of inverses, if the composition of them returns x. But they give you a nice little hint. In other words, m and g are inverses, and they want you to find m prime of 4. All right, so if m and g are inverses, that means m is equal to g inverse, and you can write that the other way around. G is equal to M inverse. I want to choose the one that allows me to differentiate G's, and I'm also looking for M prime. I'm not looking really for M inverse prime. And for that reason, I'm going to go with this connection, that M is G inverse. And so I'm going to come over here. I'm going to say in a little bit more formal, M of X is G inverse of x, which means the derivative of m, m prime of x. And I like to do derivatives of inverses with a little memorized formula. I generally don't like straight memorization for math and memorizing formulas. However, this is one case where I think it is a little bit more efficient to do. So the derivative of an inverse function is 1 over g prime of g inverse of x. And then finally, we will plug in 4. M prime of 4 is going to be 1 over g prime of g inverse of 4. And now we start pulling that off the table. And for g inverse of 4, that means you read the table backwards. You're looking for where g is equal to 4, and that happens at 2. So because g of 2 is equal to 4, we can conclude that g inverse of 4 is equal to 2. So this is going to be 1 over g prime of 2. And g prime of 2 is 0.4. So we get 1 over 0.4. And I'm going to stop right there. I'm not going to try to clean that up. I don't see any need. So moving on to part D. We are dealing with g and h this time. And we have a function j. And I want you to find j prime of 1/3. J is a quotient. And this is going to be a little bit of an ugly quotient. J prime of x, that's not a prime there. Now j prime of x is low d high, so h of 3x. D high is a chain rule, g prime of 6x times 6. So that's low d high minus high, which is g of 6x. D low would be h prime of 6x, 3x. Let's make, oh gosh, that was a huge eraser. H prime of 3x times 3. So that's low d high minus high d low all over. Low low, which will be h of 3x squared. And now I'm going to plug in 1/3. So j prime of 1/3 is going to be h of 1, g prime of 2 times 6 minus g of 2, h prime of 1 times 3, all over h of 1 squared. And I think I did all that right. Yes, I did. And now we have to pull these values either from the table or from the graph. And so h of 1 right here is going to be negative 1/2. G prime of 2 is 0.4 times 6 minus g of 2 is 4. H prime of 1 would be the slope right here, and that is a slope of 1/2 times 3 all over, where am I? H of 1, and H of 1 was negative 1/2 squared, and I am not going to clean that up. Even though you have a calculator on the AP exam, there's still no need to clean that up because it does not ask you for any type of interpretation or anything of that nature. So moving on, there is now an E and an F. Part E is a limit. I see that that limit is a fraction. And very quickly, I'm going to do what I think is the easiest part of the fraction. And h of 2, if I find the limit as x approaches 2, here's h, I will get 0. And because I'm dividing by 0, I'm going to assume this will be an indeterminate form. And so I'm going to establish L'Hopital's rule. And on a free response question, you establish L'Hopital's rule, the conditions to use L'Hopital's rule, by limiting the numerator and denominator separately. And if you did f of 2 minus the natural log of 10, f of 2 would be natural log of 10 minus the sine of pi, which is 0. So that ends up being 0. And that's, so I know my top is 0. I'm going to have to now establish the limit as x approaches 2 of my denominator is also 0, which it is. Both sides of 2 are approaching 0. Therefore, we can use limits, or we can use LOP. Therefore, limit as x approaches 2 of the original problem, f of x minus natural log of 10 over h prime, h of x is equal to, so that's indeterminate, so that would equal the limit as x approaches 2 of the derivatives of top and bottom. So the derivative of the top is going to be f prime of x. The natural log of 10 is a constant, so that will zero out when you find the derivative. And then the derivative of my denominator would be h prime of x. And f prime of 2, here we actually get to use a previous answer. F prime of 2 was part A, and that was 1/2 plus pi over 2. So I can actually bring that in. 1/2 plus pi over 2 divided by h prime of 2. And at 2, h has a slope of 1/2. That is a linear segment, and there's really no need to clean that up. That does reduce to 1 plus pi, but I really don't care. All right, then last question, for last part of question 1. let h be the velocity. So now we're looking at h in the concept of, or in the context of particle motion. Units are centimeters per second. Particles moving back and forth on a horizontal track for 8 seconds. At x equals 1 is the particle's speed increasing or decreasing. And if something is increasing, if the speed is increasing, that means velocity and acceleration have the same sign. And decreasing means they have opposite signs. So I will need to evaluate the velocity at 1 and h of 1. And if they are the same, if they have the same sign, speed increases. And if velocity and acceleration have different signs, speed decreases. Okay, so I'm going to find my velocity at 1, which would be h of 1, and h of 1 is negative 1/2. That's less than 0. V prime of 1 is going to be the acceleration. Actually, I'm going to go back. I'm going to undo that. So my acceleration at 1 would be the derivative of velocity at 1, which would be the derivative of h at 1, and h is the thing I'm looking at. The slope at 1 is positive 1/2. My velocity and acceleration have opposite signs. Therefore, so v of 1 and h of 1. Nope! Dadgum, I'm off. V of 1 and acceleration at 1 have opposite signs. Therefore, speed decreases. There we go. Woo, I feel like I blundered my way through that. Hey. Okay, let's move on to question 2. This one's going to be a lot quicker. We have a differential equation. Here, the point g of 1 equals 3.5 satisfies the differential equation. I'm going to write that as an ordered pair. I don't know why. It just makes me feel better. It feels like I'm doing something. Write the equation of the line tangent. The instant you see that, you should think point and slope. Okay, the point was explicitly given to you, 1 and 3.5. My slope is going to be the value of the derivative, which they gave you, dg dt, at the point 1, 3.5. And here's where you have to be careful. T is my independent variable, yet this derivative is given in terms of g. And so the value of g is 3.5. So I'm going to evaluate dg dt at the point when g is equal to 3.5. And that would give me 12 times 1 plus 2 times 3.5 would be 7 to the 2/3. And I'm going to clean that up because I'm looking at part B. I have to use this question to approximate g of 0.9, and simplifying this would make it a little bit easier. 8 to the 2/3 is going to be 4, and so I get a slope of 48. And so now I can write the equation of my tangent line, y minus 1 equals slope 48 times x minus, I just did that wrong. It's y minus 3.5. 3.5 was my y coordinate, so let's fix that. There we go. And there is your tangent line. Then use that equation to approximate g of 0.9. Now here's, so g of 0.9 is going to happen, let's see, so I'm going to move that 3.5 over. 48 times x minus 1 plus 3.5. So g of 3.5, g of 0.9 is going to be approximately, and I would encourage you to be careful with your symbols there. This is not equals, this is an approximation. Sometimes you will lose points on the AP exam for misusing those symbols. They didn't penalize you last year, but they have done it in the past, so I have been told. So this will be approximately 48, and we're simply plugging 0.9 into that tangent line we just had. You can stop there. You will have a calculator, negative 4.8 8 plus 3.5. If you want to clean this up, you could. There is no real value in doing that. As a matter of fact, it only allows you to look at it and feel good about it. You get the same number of points on the AP exam for the unsimplified version as you do the simplified version. So there's that. Moving on to parts C and D. Part C, find the second derivative, and I added on this in terms of G. That is typically on the AP exam. The writer of this question just forgot to put that in there. So we have dg dt. If I want the second derivative, we'll simply do the derivative of that function, which this would be a chain rule. And so that would be, we'll bring down to 2/3. 2/3 of 12 is 8 times 1 plus 2g to the negative 1/3 times 2, because that's the derivative of the inside. But remember, this is a derivative with respect to t, and g is not a t, so you have to tack on the dg dt. G gets that implicit treatment, so I have to put that in there. And if I want the second derivative of g in terms of t, in terms of g, dg dt doesn't work. I now would have to replace dg dt with this. And so now this would equal, I'm going to go ahead and say 8 times 2 is 16. I'm actually going to clean this up a little bit because I see at t equals 1, I'm supposed to plug this in when t equals 1 in a little bit. So 8 times 2 is 16. I'm going to move that negative exponent to the bottom, 1 plus 2g to the 1/3. And then I'm going to replace dg dt with the equation for the differential equation. 1 plus 2g 2/3. So there is my second derivative. Then it says evaluate this thing at t equals 1. And there's two ways you can do this. I'm almost wishing I didn't tack on that in terms of g here, because there's a quick way to do this one. So this derivative at t equals 1, you do have to remember that when t is equal to 1, g was equal to 3.5. So that's the ordered pair 1, 3.5. And that's important because my second derivative was in terms of g. So I'd actually need to plug in 3.5 for my g's. And so it's going to be 16 over 1 plus 2 times 3.5, which will be 7 to the 1/3 power. And then right here, this is my first derivative. And I've already established in part A that my slope, my dg dt at that point is 48. So I can actually import that slope that I found in part A and use it right here. So instead of doing all of that, I'm just going to say times 48, because I know that dg dt is equal to 48 at this point, and I would stop right there. And that is all of question 2. So that one was significantly faster than question 1.